And now we have section 8.4 on series for college algebra. This will be the last lesson in this class. So following this, we'll have a review and then the final exam. Here we go, series. So series are closely related to sequences. You may want that formula sheet that I have posted with section 8.3 and 8.4. It's on arithmetic sequences, geometric sequences, and we're going to use some formulas again today. So the difference is that a series is the sum of a sequence. So when you have that whole list of numbers out there, you might want to actually add up that whole list of numbers. And so that's where we can use series. So they're all on the same formula sheet. That's what the S's are versus the A sub n. So we're going to be able to find the sum of a finite series, talk a little bit about what sigma notation is and what that means, and then find the sum of an arithmetic, geometric, or infinite series. So here we go. A series is a sequence with plus signs in it. So really it's just a sequence. An infinite series is going to have a dot, dot, dot on the end. And if that is an arithmetic sequence, we cannot add all those up because it's just going to keep getting bigger and bigger and bigger, or smaller and smaller and smaller. But with geometric, we can. So we'll look at that in a little bit. So to start off with, we're going to find the sum of the first 6 terms of the sequence. So if this is a nice small number, we can just figure out what the sequence is. 32, 8, 2. What is happening here? Looks like we are dividing by 4, dividing by 4, dividing by 4. So 2 divided by 4 is 1/2. 1/2 divided by 4 is 1/8. And 1/8 divided by 4 is 1/32. And it says find the sum. So then I would probably use my calculator and add all of those up. So 32, 8, 2, 1/2, 1/8, and 1/32. And then if you hit math, enter on a TI calculator, it will give you 1365 over 32. That would be the fraction, or it's 42.65625. So that means it's 42, and we could subtract 42 and have the 0.65625. Do the math, enter on that, and you get 21 over 32. Or anyway, any of these 3 answers are correct. All right, so sometimes we don't want to have to, we don't want to have to like write them all out and add them all up. So we have some formulas for that, which we're going to use in a minute. But real quick, can you tell me what the sum of the numbers from 1 to 100 are? Pause the video, see if you can answer it, and then I'll show you. So we are doing So you can type these all in your calculator, but that might take a little while. So there is a little shortcut, and I'm just going to show you real quick how this formula came to be. This is an arithmetic sequence, and we are adding them all up. So if you're looking at your sheet at all, we're looking at the sum of an arithmetic sequence. There's 2 different formulas. You can use either one. But basically, it goes like this. You take the first plus the last, you add them up. That's 101. And then if I did 2 plus 99, that's also 101. And 3 plus 98, that's also 101. So how many 101s do I have? Well, since I'm pairing up my 100 terms, I only have 50 terms times 101. The answer is 5,050. If you add all these up and you don't make any mistakes in your calculator, you will get 5,050. So little shortcut. It's a lot faster than typing them all in. Here we have that formula. This is what I just did. This is the first term plus the last term times the number of terms over 2. And the reason we're dividing by 2 is because we took the first and last, so we kind of have to average those out. Basically, it's adding up all of the averages. So there's the formula. It's on your sheet. There is a second formula on the sheet, and that one can work too. It just kind of depends. This one you have the first and the last term. In the other formula, you only have the first term and the common difference. So it works the same way. You just have different parts to plug into it. So here's our first application. You have an automobile valued at $30,000, depreciated over 5 years. This is called the sum of the year's digits method. which you may or may not ever see again, but that's okay if you do accounting maybe. Under this method, annual depreciation is found by multiplying the value of the property by a fraction whose denominator is the sum of the 5 years' digits and whose numerator is 5, 4, 3, 2, 1. So because it's over 5 years, if this was a different number of years than these, this would be different. First of all, we have to understand what that means. It says the numerator is 5, 4, 3, 2, 1, and the denominator is the sum of 1, 2, 3, 4, 5. What is 1 plus 2 plus 3 plus 4 plus 5? Well, it is 15. So if I do 5 fifteenths, 4 fifteenths, 3 fifteenths, 2 fifteenths, and 1 fifteenths, if I add all of these up, I'll get 15 fifteenths, which is 100%. So basically I'm taking my item and depreciating it. And because this is 5 fifteenths, I'm going to depreciate it a little higher the first year, and then it's going to go down and it'll only be depreciated a little bit at the end. So this is the sequence that represents the parts of the automobile that depreciate each year. That's done with commas. Show that the sum is 100%. So if you add that up, you get 15 over 15, which is 1, which is 100%. So that's part A. Find the yearly depreciation and show that the sum of the depreciations is 30%. So each year you would take 5 fifteenths times 30,000. Then you would take 4 fifteenths times 30,000 for the second year, and third year, and the second year, and the first year, or fifth year, so on. Sorry, went the wrong direction. And then you could just add up all those answers and make sure they're right. So let me show you what that looks like. We already answered part A. Part B. Here are each of the years, 1, 2, 3, 4, 5. And if you add up all of these numbers, you get 30,000. So we fully accounted for the full value of the car. You can also use the sum of arithmetic sequence formula. The first year was 10,000 and the last year was 2,000. And there are 5 terms divided by 2 always, and it came out to 30,000 also. So that's just another way to show that they add up to the same thing. Okay, if I want to look at a geometric sequence, this is the formula that I would use right here. R can't equal 1 because if R is 1, it's not a geometric series. If you keep multiplying by 1, you're just getting the same number over and over and over again. So that doesn't make any sense at all. So in order to use this formula, what do I need to know? I need to know the first term, the ratio that I'm multiplying by, and how many I'm looking for. So the sum of the 10th terms, would that be a 10th? Whatever, however many you're looking for. Oh, look, 10 terms. Find the sum of the first 10 terms. So that's telling you that n is 10 of the geometric sequence with the first term, a1 is 5, and the common ratio of 2. So the formula they gave us is s sub n is a sub 1 times 1 minus r to the n over 1 minus r. So my first term is 5, 1 minus negative 2 to the 10th over 1 minus negative 2. Careful with those double negatives. And that will be the sum of the first 10 terms. So the notation there, you do s sub 10 is, let's figure out what that is. Make sure you're careful with your parentheses. When you type this in, you actually need to put parentheses around the top and parentheses around the bottom if you're doing it all at once. So 5 times 1 minus parenthesis negative 2 to the 10th, close, divided by, well, you could do that in your head. 1 minus negative 2 is 3, but be careful with your negatives. And I typed something in wrong. There we go. I got negative 1705. So just be really careful when you put that in. Just checking my answer, it's right. All right, here we go. Let's try another one. Find the sum of the first 8 terms of this sequence. So 8 terms means I'm looking for s sub 8. First term is 2. 1 minus, what is my common ratio? They didn't tell me this time. What am I multiplying by? Half. Half. So you can do 1/2 or 0.5. I'm looking for the 8th term. So this is an 8. over 1 minus 1/2. I'm going to simplify that before I type it in. Let's do 1/2 to the 8th power. 1/2 to the 8th power, just to see what that is. I don't really want to write that way. I'll just keep it as 1 minus 1/2 to the 8th power over 1 minus 1/2 is 1/2. So 1 minus 1/2 to the 8th power divided by 1/2 times 2. I forgot to put that part at the beginning. So I got 3.984375. If I turn that into a fraction, it's 255 over 64, which is more accurate because otherwise I rounded my decimal a lot. And so fractions are better, but whatever. If I say round to the nearest third decimal, then that first answer would be right. All right, here's an example using money again. So we have regular payments of $1,200 are made at the end of each year for 4 years into an account that pays 10% interest compounded annually. The future value of this annuity is $55,650. So you would take that $1,200 times 1 minus the rate on this. Because it's interest of 10%, your rate is 1.1. Because you have to have 100 plus the 10%. You're doing it for 4 years. So here's the formula. It's exactly the same. Finding S sub 4, we take the first term times 1 minus the rate to the number of years divided by 1 minus the rate. Exactly the same formula. Type that in. You may recognize this formula from when we did interest in lesson 6. Nope, chapter 5. It was in chapter 5 when we did this formula a bunch. All right, one thing that's kind of cool about infinite geometric series is you can actually add them up sometimes. So example, if I have a geometric series that starts with 8, 4, I'm going to make it a series and add them up. 2, 1, half, 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 half. What am I adding here? I'm adding smaller and smaller and smaller and smaller. I'm adding so little that it's just going to get tiny. So if I graphed this and I started at 8, let's just start down here. Say that's 8. Then I'm going to add 4. And I'm going to add 2. And I'm going to add a half, 1, and then a half. And I'm just adding a little bit less, more and more and more and more and more. Tiny little fractions that I'm adding. It's going to have this place where it's never going to go past. And eventually, if I went all the way to infinity, that's the sum of the infinite series. So I'm looking for that number. It's different for each series. If these numbers are getting bigger and bigger and bigger, if I did 8 plus 16 plus 32, double, 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 this is getting huge. There is no limit. So in order to find the infinite one, and this is also on your formula sheet, you just got to look for the one that has an infinity sign. If the R value is bigger than 1, then it does not exist. The R value that you're multiplying by has to be less than 1 in order to have an answer on these. So let's try this one out. Find the sum represented by the following series if possible. It's supposed to be infinite. That's what I thought. So it's supposed to have plus dot, dot, dot. If this was infinite. So let's see, what's R? R is, what am I multiplying by? 1/6. Divided by 6, divided by 6, divided by 6. So since my R is less than 1, I can use the formula. The formula for the infinite series is the first term divided by 1 minus R. And that's it. It's actually it's even more simple formula than we were using a minute ago. So you divide that and you get 43.2. You can kind of check it in your calculator too. You can do 36 plus 6, 36 plus 6 plus 1, and then you're going to add 1/6 and then add 1/36, and you'll see that you're just barely adding any at all anymore. And you're never going to go over that 43.2. It's going to look like it gets there pretty fast, but it's not going to go past it. So you just use that formula. Okay, this is called summation notation. We haven't really looked at that. It's sigma, and it means the sum of the terms, term number 1 through infinity of this function. So the first term, you plug in a 1. When I plug in a 1, I get 3/5 to the first power. When I plug in a 2, and you just step up, plug in a 2, you get 3/5 to the second power. When you plug in a 3, you get 3/5 to the third power. And when you stop, when you get to infinity, so that means this goes on for infinity. Because it's sigma, it means it's plus. It's the sum of all of these terms when you start at 1 and end at infinity. So what would this be? Well, I can write it out this way so to kind of see what my series is. I can also use the formula. So the sum of this infinite series is first term, which is 3/5, divided by 1 minus the rate. Well, what's the rate? If every time I'm increasing my exponent, then what am I multiplying by every single time? I'm multiplying by another 3/5. So the answer to this problem is 3/5 divided by 1 minus 3/5, which is 1.5. So if I kept adding up all these fractions that are getting smaller and smaller and smaller and smaller, I'm going to reach 1.5. We'll almost reach it. All right, one more thing about that sigma notation. Just give you another example. They can use any letter they want right here. Usually they start at 1. They don't always. They can stop at a number or infinity. And then they'll have some kind of formula here. So here's an example using sigma notation. So if I gave you this problem right here, what it's asking you to do is find the sum of the values when you plug in a 1, 2, 3, 4, and 5, and then add them up. That's it. So the first term, when you plug in a 1, you get 2 times 1 squared. When you plug in a 2, when you plug in a 3, 3. When you plug in a 4, and you stop when you plug in a 5, but you do still do it, and then you just add all those up. That's what that means. So this notation, this is where you start, this is where you stop. You always go up by a whole integer, no decimals, and you plug that number in for whatever letter they use, you just plug it in there. So that's sigma notation if there's any others like that. And then this sum means add them up. So don't just list them, you got to add them up and get the total also. All right, that finishes up lesson 8.4. So go ahead and work on the homework and let me know if you have questions, and then we'll have a review and a test.